Oh, there we are. Okay, good morning, lads and ladies. Welcome back to Calc 2. Today we are going to continue talking about power series as promised. Some of your tests are graded, most of them are not. The truth is I just have not had time. It's tricky grading 4 versions of the same test. And I think I even have some people who haven't taken it yet. I've got one person taking it Monday. But we're getting there, and I promise over the weekend they will all be done. So I do apologize for the time it's taking, this scheme of allowing everybody to do a makeup test and then also allowing everybody to do it in 2 different places results in 4 different tests, which is way harder to grade than a single paper test. But I don't want to sit here making excuses, just want to apologize. Let's, there we go, let's launch this and we can get started talking about power series. All right. So I know this is an intimidating topic. I don't have a great feel for how you guys are doing with it. So before I launch into Taylor's theorem, which I think generally takes a good bit of patience and understanding to learn how to work with, I would like to take a few homework questions. So I'm going to pop over to WebAssign, and you guys can ask questions from any of the chapter 11 homework stuff that you'd like to see. I would be happy to work any of those problems to try and fill in any gaps, any places before we get into Taylor's theorem. Good news, Taylor's theorem really is the last thing even related to series that we're going to talk about. So once we are comfortable with the Taylor formula and Taylor polynomials, we will be done with series. So here's the current homework set. I'll go ahead and pop that. You guys could let me know in the chat what you would like to see. Let me turn this off. Then I would be happy to look at any problems you want to look at. Or if you don't know a specific problem, you just want to tell me a problem type, we can do that too. Meanwhile, I'll do this. This is my 2312 section 004. I should say Calc 2. And today is the 12th, right? 11th or 12th? 12th, yeah. Okay. Yeah, I will focus here. This camera is drifting. There we go. All right, so normal stuff. This is Calc 2. Today is the 12th of November. Today we're going to get some more practice with power series, of course, 11.8 and 11.9. And we're going to introduce Taylor's theorem. So let me know in the chat. Any problems you'd like to discuss? That's where we're going to start today. Did I just turn that shit off? Why is this? Oh, it's loading one at a time. All right. So I did get a request through DM to go ahead and do problem 1. I can do that for you. That's not a problem. We're asking for the radius and interval of convergence for this power series. And if the rest of you would just take the time to let me know what problems you want to see discussed or worked through, then I will work through them. We will spend the first half of class doing this today. So the series here, you've got some constant, maybe 2, maybe something else, times -1 to the n and x to the n. And we're summing from 1 to infinity. We want to find the IOC and ROC. So this is what homework number is this? I forget, 11. Yeah. Like that. Homework 11, problem 1. Find ROC and IOC for the series sigma n equals 1 to infinity 2 times negative 1 to the n n x. And we'll do 12 after this. So I do want some interaction. If you guys could please tell me, where do we even get started? I'm looking, I've got a power series. I want the radius and interval of convergence. What do I do? Oh, interesting. I hope things are if you're having fun down in Puerto Rico. Yeah, I'll upload that lesson. I did see this morning that that it's not uploaded yet. I will upload it as soon as I can later today. Okay, so who can help me out? Where do I even get started with this thing? Good, ratio test, right? Kylie's correct. We're going to use the ratio test. It's not a geometric series because of the n here, right? If it was just negative 1 to the n times x to the n, then I could attack this as a geometric series and skip doing any ratio test work. But because that n is there, we need to use the more general approach. And the more general approach is the ratio test. So L is, as always, the limit n to infinity, the absolute value an plus 1 over an, where an is just the whole thing inside the series, whatever this stuff is. So we're going to crunch out this limit, and that's going to give us some, expression in terms of the absolute value of x. And then we're going to set that less than 1. And we'll try to solve for x. So here, that limit is lim n to infinity, absolute value of, here's an plus 1. And I need to divide by an. Okay. And the trick to sorting out this limit is we can cancel the 2's. And then we put all the other pieces together, right? And kind of clean up as much as we can. So I get lim n to infinity, absolute value of negative 1 to the n plus 1 over negative 1 to the n times n plus 1 over n times x to the n plus 1 over x to the n. Which is then n to infinity. Absolute value of negative 1 to the n plus 1 divided by negative 1 to the n is negative 1. N plus 1 divided by n is just n plus 1 divided by n. There's not much we can do there. X to the n plus 1 over x to the n is just x. And I can take the absolute value of each of these pieces separately. Since n plus 1 over n is certainly positive and is going to infinity, right? There's nothing negative here. He is just going to be himself. The absolute value of negative 1 is 1. This is going to go away. The absolute value of x is going to stay. I will pop the absolute value of x outside the limit because it doesn't have any n's in it. I'm left with lim n to infinity of n plus 1 over n. What is the limit as n goes to infinity of n plus 1 over n? What is this piece? Very good, it's 1. Right, you can think of it as a L'Hopital rule thing. You can think of it as a renormalization thing. You can think of it as a ratio of lead coefficients thing. However you get there, this limit is 1. At this point, we should be very comfortable with that. So that means that the limit L from the ratio test for this power series comes out to the absolute value of x. And remember what the ratio test says. It says if L is less than 1, then the series is guaranteed to converge absolutely. So our power series is, I can never spell guaranteed, right? G-A-U? Whatever that word is spelled correctly, guaranteed to converge absolutely, provided L is less than 1, which would mean the absolute value of x is less than 1, which means -1 is less than x is less than 1. So I can sketch my interval of convergence. The series is centered at 0, and the endpoints for the IOC are -1 and 1. And the series is guaranteed to converge absolutely for any x value in here. The question is, what about the endpoints? So definitely converge in here. But what about here? Or here? Right? If I stay strictly between -1 and 1, I know that the series converges. But what about at 1 or at -1? Those are the numbers that make the ratio test limit L, which is the absolute value of x, equal to 1. And we know the ratio test is inconclusive when L is equal to 1. So we need to test these separately. And this is sort of how these problems go in general. You run the ratio test. That will tell you the radius of convergence, basically, right? What we've learned here is that the radius of convergence is 1, the distance from the center to the endpoint. Now we need to test those endpoints. If I plug in -1 to my series, it becomes sigma n from 1 to infinity, 2 times -1 to the n times n times -1 to the n. And you can probably smell it already. The 2 pops out. You get -1 to the n times -1 to the n, which is -1 to the 2n times n. -1 to the 2n, an even power of -1 is just 1. So this is 2 times sigma n from 1 to infinity of n. Does this series converge or diverge? This series convergent, divergent? Yeah, massively divergent, right? That's correct. Why? Why does this series diverge? What test could I cite? What's the simplest test that would show the series to diverge?
The test for divergence.
Yeah, very good. the limit as n goes to infinity of the ANs here is the limit as n goes to infinity of n, which is infinity, which is very much not zero. All right, so if the limit of the ANs is anything other than zero, the series automatically diverges. This motherfucker diverges about as hard as a series can. It's not even trying to converge. And we'll see something similar at +1. If you plug +1 into that power series, you get sigma n from 1 to infinity, 2 times -1 to the n times +1 to the n, which is 2 times sigma n from 1 to infinity. +1 to the n. +1 to the n is just 1. So this is just -1 to the n times n. And this also diverges by TFD. Same test for divergence. Here, the limit as n goes to infinity of the ANs is the limit as n goes to infinity of -1 to the n times n. What is this limit?
This also diverges.
It's true. It's true. The series diverges, right? But what can we say about this limit? Or maybe you mean that the limit diverges. That's not quite the language we would use. It's true that the sequence AN here diverges, which would imply divergence of the series, but we want to be very careful with our language.
It goes to infinity.
I got two comments that came in at the same time. The n piece does go to infinity. That's correct. What does the -1 to the n piece do?
Swaps between positive and negative.
Yeah, so for large values of n, this thing is like plus big number minus big number, plus big number minus big number. The limit of the sequence does not exist. The limit -1 to the n times n does not exist. And that's very different from existing and being zero. This reminds me, I created a new tool in Desmos that I'd like to share with you guys. Something you can play with to help you visualize what's going on with sequences. Let's see. So if you're having trouble visualizing or conceptualizing sequences, this is a neat tool for you. Don't worry about any of this stuff. The idea is just here that you can type in any function and it will give you the sequence that you get from that function. So here, if we wanted just the sequence n, the black dots are the terms of the sequence. There you go. I don't know how it will handle -1 to the n times n. Oh yeah, not bad. So what we see is that those black dots, some of them are going up to positive infinity, some of them are going out to negative infinity. They're definitely not getting closer and closer to any particular number. Oh, I wrote n's here, huh? Should be putting x's. There we go. That's why it's doing that weird shit. Pretty neat, right? So yeah, this is definitely not a convergent limit. The limit of this sequence does not exist. Half the time it's jumping down to negative infinity, the other half the time it's jumping up to positive infinity. So the test for divergence works at both endpoints to show that the series diverges. There was a comment in chat that the series in question here is an alternating series, and that's true. That's true. But remember, the alternating series will never tell us that a series diverges. Alternating series test can only ever say under some conditions, right? The BNs are decreasing and the limit of the BNs is 0. Under those conditions that the alternating series converges. So if you're trying to show that an alternating series diverges, you need something other than the alternating series test. All right. Since the series diverges at both of these guys, right? Diverges at +1, diverges at -1. The IOC cannot include either of those. It must be the open interval from -1 to 1. So that is the interval of convergence for this power series. Radius of convergence was 1. Interval of convergence is the open interval from -1 to 1. All right, we did have a request to look at number 12. I will do that now. And real quick, let me share with you. Let me put something else that's a little more fun in here. What I had before cosec's. How about sine x over x? This is a fun one. So this would be the sequence sine n over n. I'll save this and drop this in the chat if you want to play with it. It's a fun way. If you're having trouble figuring out the limit of a sequence, this can be a really fun tool to help you with that. I built it to help my wife see why this sequence diverged. Anyway, number 12. Ah, yeah, that's a doozy, isn't it? So here we have some factorial-like products in our power series. And what you're going to see as we get into section 1110 is that power series often have these factorial-like products. So let me write this down. Same thing. We want IOC and ROC. So this is homework 11, number 12. Find the ROC and IOC for the power series sigma n from 1 to infinity. N factorial x to the n divided by this bizarro looking product, 7 times 15 times 23 all the way out to 8n minus 1. Just for fun, let's write out the first few terms of the series. When you plug in n equals 1, you get 1 factorial x to the 1 over 7. Plus. When you plug in 2, you get 2 factorial x to the 2 over 7 times 15. You plug in 3, you get 3 factorial x to the 3 over 7 times 15 times 23. The next term here would be 4 factorial x to the 4 over 7 times 15 times 23 times. The next term in this product would be 31, right? We're going up by 8 each time. So that's what the first few terms of this series look like. Intuitively, what's going on here, there's an n factorial upstairs, and there's this weird factorial-like product downstairs, and those guys are fighting each other. The n factorial upstairs wants to make things big, which would hurt the convergence of the series. The factorial-like product in the denominator wants to make things small, which will help the convergence of the series. As always, I'll run the ratio test. L is the limit. As n goes to infinity, absolute value of an plus 1 over an. That is lim n to infinity. An plus 1 is n plus 1 factorial x to the n plus 1 divided by this product out to n plus 1, which would be 7 times 15 times 23, 8n minus 1, and then the next term would be 8n plus 1. minus 1, or 8n plus 8 minus 1, which is 8n plus 7. So there's an plus 1. And we've talked at length about how to handle these products downstairs. Remember, the idea is you want to write the second to last term, which is the last term of an, and then the term that comes after that. And the pattern here is that the next term in the product is just 8 plus the previous term in the product. So 7 plus 8 is 15, plus 8 is 23. So to go from 8n plus 1, you would add 8 and you get 8n plus 7. Or you can think of it as replacing the n in parentheses by n plus 1. Sure, we'll look at 13 afterwards. All right, so that is an plus 1. Now I'm going to multiply by the reciprocal of an, which is 7 times 15 times 23 up to 8n minus 1 divided by n factorial x to the n. And that is my ratio test limit. I'll group the similar looking terms together. So we have n plus 1 factorial over n factorial. We have 7 times 15 times 23 out to 8n minus 1 over 7 times 15 times 23 out to 8n minus 1, 8n plus 7. And then x to the n plus 1 over x to the n. And there's lots of cancellation in these factorials and factorial-like products. N plus 1 factorial over n factorial. At this time, we should be pretty comfy saying that is just n plus 1. I'll write it out, why not? N plus 1 factorial is n plus 1 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. N factorial is just n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. I've got my 1 over 8n plus 7. The surviving term from this ratio is just that. And x to the n plus 1 over x to the n is just x. Here, like we said, n plus 1 factorial over n factorial is going to cancel to just n plus 1. So I'll pop out the absolute value of x. Inside left here, lim n to infinity, n plus 1 over 8n plus 7, which is positive. So I'll lose the absolute values there, although it doesn't matter. Keep them or not, just makes it a little cleaner to write. Okay, what is this limit?
One over 8.
1/8. Again, either by L'Hopital's rule or by renormalizing or by comparing the coefficients. So what we get here is the absolute value of x times 1 over 8. So before I move on, and I will finish this, but before I move on, who's stronger, n factorial or this weird product downstairs? We said the n factorial wants to hurt the convergence. The product downstairs wants to help the convergence, and our ratio test limit came out to this. Before I make any deeper statements, can you tell me who wins? N factorial or the weird product downstairs? Who grows faster? Who's tougher?
The downstairs product.
The downstairs product, right? Very good. The downstairs product is growing faster than the factorial. If this limit came out to just the absolute value of x, then it would basically mean that the factorial and the thing downstairs are growing at the same speed. But since this came out to absolute value of x times 1/8, that means that the downstairs is winning. He's growing faster than the factorial. All right. So L from the ratio test is the absolute value of x over 8. Thus, the series, the power series, will converge absolutely. Provided L is strictly less than 1, which means the absolute value of x over 8 is strictly less than 1, which means the absolute value of x is less than 8. Pause here. What's my radius of convergence?
8.
8. Very good. All right. Once you arrive at this step, you know that this number is your radius of convergence. Now we can continue. Say this is equivalent to -8 is less than x is less than 8, and sketch our IOC series again, send it at 0. If you like to sketch the IOC before stating the radius of convergence, that's totally understandable. But you can verify here that your radius of convergence is 8. Distance from the center to the endpoint. We do need to check the endpoints. I'll do that on a separate sheet here. So when x is equal to -8, we have sigma n from 1 to infinity, n factorial times -8 to the n over this weird product. And this guy is a little cattywampus. Not immediately obvious what to do with this thing, is it? Yeah, I won't lie. It's not jumping out at me right away. With all of those factorial-like things, I'm tempted to say we should run the ratio test, but we know that the ratio test limit here would come out to 1. So this is -1 to the n, n factorial, 8 to the n over this weird product. Yeah, I have to think for a minute here. I guess we could use the alternating series test. We could try taking a limit. Yeah, I won't lie. It's not jumping out at me right away. This is a challenging thing to do. So when all else fails, if you're stuck, this is a good teachable moment. When all else fails, if you don't know what to do, think about our strategies from 11.7. We should run the test for divergence in our head if possible. If we can't sort it out in our head, then we should write it out. If that fails, then we should try to classify the series according to its form. Normally, we would do the ratio test because of the factorials and factorial-like products, but we know the ratio test is going to fail us on this because the reason we're plugging in -8 is because we know that that will make the ratio test limit equal to 1, right? This would be 1 if we plug in -8. So the ratio test isn't going to save us. That pretty much just leaves for this guy some sort of comparison or an alternating series test. The test for divergence limit isn't clear right away. So let me write it out. When n to infinity of an is when n to infinity, -1 to the n, n factorial, 8 to the n, 7 times 15 times 23 out to 8n minus 1. So this limit will either be 0 or dn, right? Because of the -1 to the n here. If this stuff doesn't go to 0, then the whole thing would bounce back and forth between whatever non-zero value it goes to. So what we need to ask ourselves is, does n factorial times 8 to the n divided by 7 times 15 times 23 out to 8n minus 1, does that go to 0 or not? I would love to use this as an example to fart around with my Desmos environment, but because of that weird product, I don't know if we can. I can try the multifactorial notation, see what that does. Let's see here. I'm going to say x factorial, that's already going to give it a hard time, times 8 to the x divided by 8n minus 1. How many factorials would that be? The 8 factorial, 1, 2, 3, 4, 5, 6, 7, 8. And Desmos says, no way. Not surprising. Well, we can compute some values here and start trying to get a feel for it. What else could we do? What else can we do? L'Hopital's really going to save us because there's no differentiating that or that. Can we factor anything out of this product? All right, no common divisors between 7, 15, and 23. 7 and 23 are prime. I don't know why. I don't see this right away. I genuinely don't. Yeah, this is a hard limit to work with. What can we do? Well, how many terms are there in the product downstairs? Let's see. All the way out to 8n minus 1. So there's going to be n terms in the product downstairs. I could start splitting this up as 1 over 7, 2 over 15, 3 over 23, all the way out to n over 8n minus 1. Let me try that. So here's an interesting thing, right? This is a place where it's good that we wrote out the first few terms. So see, the first term of the series, that product with n equals 1, has 1 term, 2 terms, 3 terms, 4 terms. So the product downstairs, this guy, we can see pretty readily has n terms in it, right? When n is 4, you've got 4 terms. When n is 3, you've got 3 terms. So what I'm going to do is I'm going to take the factorial and I'm going to split it up and give each piece downstairs a piece of the factorial. We can see what that does. So the negative 1 to the n times 8 to the n chilling. N factorial, I will write as in ascending order, 1 times 2 times 3, all the way out to n minus 2, n minus 1 times n. And downstairs here I have 7 times 15 times 23, all the way out to, what is the third to last term in this product? 8 times n minus 2 minus 1, which is 8n minus 16 minus 1, which is 8n minus 17. And then we would have 8n minus 9. And then 8n minus 1. So can we get anything out of thinking of it like this? Negative 1 to the n, 8 to the n. So it's 1/7 times 2/15 times 3/23 times n minus 2 over 8n minus 17 times n minus 1 over 8n minus 9 times n over 8n minus 1. I do think this limit is going to be 0, or at least this piece is going to go to 0. So to argue that this piece goes to 0 is not too bad. You'll notice that the latter terms in this product, like n over 8n minus 1 and n minus 1 over 8n minus 9 and n minus 2 over 8n minus 17, each of these go to 1/8. So this product, as you extend it out further and further and further, it looks like 1/8 times 1/8 times 1/8 times 1/8, which would certainly go to 0. In fact, this product right here as asymptotically 1/8 to the n, which would cancel with this and give us -1 to the n. So this overall limit here is going to be dne. And I don't know how satisfying you find that explanation. Let me try to annotate this a little bit. This is a hard problem. We'll need to think if we can come up with a nicer argument. But this piece is asymptotically, so I'll say very similar to (1/8 to the n). Because the individual terms in that product go to 1/8, and there are n terms. Right? For example, just look at this last term, n over 8n minus 1. The limit of that thing on its own is 1/8. So as you extend this product out further and further and further, you'll have n terms, all of them looking like 1/8. And that would annihilate this. So as a limit, now I'm not saying these are algebraically equal, I'm just saying the one limit is equal to the other limit. This would be -1 to the n times 8 to the n times 1/8 to the n. And that's when n to infinity, -1 to the n, which is the n. So the series would diverge at -8. By the test for divergence. And without the -1 to the n, we would get the same thing. We would just get 1 out, right? Yeah. So at x equals 8, our series is sigma n from 1 to infinity, n factorial 8 to the n over 7 times 15 times 23 up to 8n minus 1. And the TFD limit here, again, not at all obvious. I would write this as lim n to infinity, 8 to the n times the factorial, 1 times 2 times 3 up to n minus 2, n minus 1, n over that product, 7 times 15 times 23 up to same thing, 8n minus 17, 8n minus 9, 8n minus 1. And then thinking as we did here, that this product is basically 1/8 to the n, or the word is asymptotically. As n gets larger and larger and larger, the ratio between this thing and 1/8 to the n would go to 1, because each of these terms goes to 1/8, and there are n terms. This would be, by exactly that same logic, lim n to infinity, 8 to the n times 1/8 to the n, which would be 1, which is not 0. So the series diverges by TFD. Hence, the IOC is the open interval from -8 to 8. Now, before I move away from this, I do want to talk about some other stuff. Before I move away from this, I'm curious to see what the authors intend here. So let me flip this back. Oh, did they just ask for radius of convergence? No, they want the IOC. Okay, so we do need to know what happens with the endpoints. Let's see what they say. So they say when x is plus or minus 8, we get this. And they do as we did, they write out the factorial and the product downstairs. Same shit. So rather than arguing that 1 times 2 times 3 up to n over 7 times 15 times 23 up to 8n minus 1, instead of arguing that that thing is like 1/8 to the n, they distribute this 8. The 8 to the n here is 8 times 8 times 8 times 8 n times. So they give each term of this product an 8. So 1 times 2 times 3 all the way up to n, which is n factorial times 8 to the n, is 8 times 1, 8 times 2, 8 times 3, all the way up to 8 times n. And then they're grouping these. They say 8 over 7 is bigger than 1, 16 over 15 is bigger than 1, 24 over 23 is bigger than 1, and 8n over 8n minus 1 is bigger than 1. So because the terms of an are all bigger than 1, the limit of the an could not possibly be 0. In fact, you could deduce from this that the limit of the ans is going to be 1 when you plug in positive 8 and dne when you plug in negative 8. So they're actually doing the same shit. That argument feels a little bit sophisticated for this class, if I'm honest. But that does mean that you would want to think of it this way. This, I think, is probably the best way. So let me annotate a little bit here. I know that this is tricky. So what's going on in this product? Each term in this product is approximately equal to 1/8. And there are n terms. So this product is approximately 1/8 to the n. Right? And that's how we argue to get here. If you prefer the textbook argument there, you could say 8 to the n times n factorial is 8 to the n times 1 times 2 times 3 up to n minus 2 n minus 1 times n. And that would be, because you've got n copies of 8 here. So this would, you give 1 copy to each of these guys, 8 times 16 times 24 up to 8n minus 16, 8n minus 8, 8n. So that ratio, 8 to the n over n factorial divided by 7 times 15 times 23, all the way out to 8n minus 1. I'll write the last 3 terms, 8n minus 17, 8n minus 9, 8n minus 1. This would be equal to 8 over 7 times 16 over 15 times the next one, 24 over 23. Maybe I'll just write the last 2 terms here, which are 8n minus 8 over 8n minus 9 times 8n over 8n minus 1. And then what they're saying is that since each one of these is bigger than 1, this is bigger than 1 times 1 times 1 times 1 times 1. So the limit n goes to infinity of an must be bigger than the limit as n goes to infinity of 1 to the n, which would just be 1, which is not 0. So the ans, I don't even need the not 0, it's just 1. So lim n to infinity an is not 0. That's the way they get there. All right, I can see this is a tricky problem. Coming up with the radius of convergence here is not hard, but testing those endpoints is very hard. Very strange stuff. It does yield to TFD. It does yield to our sort of simplest test. But the limit in question, whoo, that limit, that is a sneaky fucking limit. All right, let me take a quick look at the chat here. We wanted to look at number 13 if possible. And then the other thing I wanted to do before kind of priming you a little bit for Taylor's theorem, and we are getting close time-wise, is an integral or two where we're writing a function as a power series and then doing the integral. So let me pull up number 13 and do a quick look-see at this guy. Oh yeah, this is not bad. 13 will go quick. So this is very much in the vein of what we've been doing the last couple of days, writing functions as power series. And this is the skill I want you guys working on now. If I were to put this particular problem on exam 3, this would be as nice as possible. This is actually a very straightforward problem of that style. What we're going to use here is the geometric series trick. One over 1 minus u can always be written as sigma n from 0 to infinity u to the n. So f of x, which is 1 over 9 plus x. Who can help me pushing this into the form 1 over 1 minus something? I want to make this look like this. What can I do to do that? What algebra can I do? Yeah, well, almost. So writing the plus as minus minus, that is something we're going to do. We can go ahead and do that at this step. That's okay. So I could write this as 1 over 9 minus negative x, and that gets me a 1 over 9 minus something, but the 9 is still a problem. Right, I need a 1 there. How do I make this 9 a 1? Starts with an F. Not a dirty word. Yeah, we're going to factor. We're going to force factor out a 9 in the denominator. So I can write this as 1 over 9 times 1 minus negative x over 9. And you usually, when I solve these for you in the last few days, you see me doing the factoring first. Either one is fine, really. Just be careful with your algebra. So this then can be 1/9 times 1 divided by 1 minus negative x over 9. And now this is in the form 1 over 1 minus u. Here's u. So by the blue geometric series trick above, f of x is 1/9 times sigma n from 0 to infinity, negative x over 9 to the n. And that's the big step. We now have a series. From here, it's just a matter of cleaning it up to make it look like the standard form of a power series. So that's 1/9 sigma n from 0 to infinity. Negative 1 times x times 1/9 all to the n is negative 1 to the n over 9 to the n times x to the n. Basic algebra rules for exponents. Gotta be comfy with that. And then I can bring the 1/9 in. One-ninth times this stuff is negative 1 to the n over 9 times 9 to the n is 9 to the n plus 1. And we have here just x to the n. And the IOC work here is simple because we only used the geometric series trick. I never did any integration or differentiation. This series is not coming from nowhere. This is a geometric series. Right? This is the thing we call the geometric series trick. the series since our series is geometric, it will converge if and only if the absolute value of the common ratio, which we've called u here, is less than 1. Which means the absolute value of negative x over 9 must be less than 1. And we've been playing these games with absolute value inequalities for a while. This is the absolute value of x over 9 less than 1. Because the absolute value of negative thing is just that thing, and then the absolute value can be split up over the fraction. So we get the absolute value of x is less than 9, i.e. negative 9 is strictly less than x is strictly less than 9. So the IOC, the open interval from negative 9 to 9, and the ROC is the number 9. You do need to become proficient with this geometric series trick. That is a necessary thing. I've said it a few times. This is like the starting point for pretty much everything we do with power series in 11.9. Since we have had a few days to talk about it, and you have had some time to fiddle with the relevant homework, are there any questions on what we did here? Totally open, right? Anything you want to ask. Notation questions, there are no bad questions. Anything at all. Don't be shy. Even if it's just, what the fuck? I just want to hear how you're feeling. Okay. Getting some DMs, I appreciate that. Yeah, you can always DM me comments or questions too, right? If you don't want to share with the whole class, I understand. Any thoughts at all? It's genuinely not too bad, but we do need to be comfortable with the notation. I think that's the biggest challenge here. But I want to hear what you think. I'll hold for just a few more seconds. Questions, comments, general feelings, just so I know where you're at. So that can help me decide what problems to put on the study guide, the homework, what to talk about on our review days. Tell me anything you're feeling or thinking about this problem. Totally open. DMs if you want to keep it quiet. That's fine. Good, thank you guys, yeah. The algebra maneuvers here are sneaky. Certainly that is true. Sort of the way I choose to think about it, I'm getting comments about the management of the constants. The way I think about it is first I make this a 1, then I make this a 1, then I make the minus show up. So if there was a number up here, or a variable like x up here, I would factor that out first. Just write it, say, suppose this is a 12 up here, I would write this as 12 times 1 over 9 plus x. That gives me the 1 upstairs that I need. Then the way I think about it is my next task is to get a 1 in this position. So I would factor out the 9, and that would get me to something like this. So maybe a little algebra note. And then I'll address moving the constants in and out of the series since there was a couple mentions of that. If you have something like A over B minus C, I can always write this as A times 1 over B minus C. And then I can always write that as A times 1 over B times 1 minus C over B. And then the B from downstairs, this is the same as A over B times 1 over 1 minus C over B. So there's a definite pattern in the algebra maneuvers that we do. And for most of these things where you're using the geometric series trick to get a power series, it'll be this sequence of steps where you kind of bring out the top, and then you factor out whatever you must from the bottom to create a 1 here. And then we just pull this guy out of the fraction, right? Everything is being multiplied. Fractions multiply straight across. So when I multiply A over B times 1 over 1 minus C over B, the A would go upstairs as A times 1, and the B would get distributed over these two, which would get us this. So the algebra steps almost always look just like this. And then if you had a plus here rather than a minus, you would write it in the last step, if this was a plus, as minus the negative. The other thing constants and sigma. If you have some constant times sigma some stuff, remember that constant can freely move in and out. The rules for sigma are the same as the rules for integrals. So for example, if I have like 2/3 times sigma -1 to the n, let me make it a -2/3, -1 to the n over 3 to the n x to the n. If I had something like this, no matter where the sum is, let's say sigma n from 1 to, or let's do 0 to infinity, because that's usually what we're looking at with power series, then that -2/3 can come inside. And then we can use regular algebra rules to put together the pieces that go together. So the 3 times 3 to the n would be 3 to the n plus 1 downstairs. -2 is -1 times +2. So I could write that as 2 times -1 times -1 to the n would be -1 to the n plus 1. And the x to the n plus 1 will show. So bumping constants into the sigma, it can, I think, again, it's really just the notation. I know you guys know these algebra rules. But remember, yeah, constants can slide in and out. What makes a constant with respect to sigma is that it doesn't have any ends in it, or whatever your index of summation is here. It's like that 9, the 1/9 here, comes inside. And then 9 times 9 to the n is 9 to the n plus 1. That's really what we're doing. And this I think where I write out every step is maybe a little easier to see. All right. Thank you very much to everybody who's brave enough to give me some comments here in the chat. And I genuinely appreciate that. That helps me help you. And I hope that we can continue with that. All right. I wanted to solve at least one more problem where we're evaluating a series or evaluating an integral by using a series. I did give you 1 or 2 of these, I think, in your homework. I'm not going to do the exact homework problems here because I do want you to work them. Let me turn off the key. Yeah, of course. So if you look towards the end here, right, we've got some problems where we want to do, here you go, 21, 22, 23. These are all evaluate the integral by writing the thing as a power series. So maybe I'll do one that's kind of like 21, and I'll do one that's kind of like 22 or 23. about x squared over 1 plus x to the 13 as a power series. So you remember way back at the end of chapter 7, we said that, as we prepared for test 1, many integrals are straight up impossible. Like you cannot find an antiderivative for e to the x over x, or sine x over x, or e to the x squared. All of those functions have no closed form antiderivative. The beauty of power series, and really the deep reason why we're doing all of this series work, is to get you to a place where you can evaluate those integrals. Sure, they don't have closed form antiderivatives. There's no finite expression for their antiderivatives, but there are antiderivatives. They're just not closed form. They're not finite in length. They require the use of infinitely many terms. I don't know if this function that I just wrote down is an example of such a thing, but the ones I'm going to do next are. And finding an antiderivative for this certainly would be a bitch and a half. But as a power series, it's actually quite easy. So what we're going to do is rewrite the inside as a power series, and this gives us an opportunity to play more with that geometric series trick. So like I said, the first thing we do is peel off whatever's upstairs. Write that out front. So that becomes x squared times 1 over 1 plus x to the 13. Now I've got 1 divided by 1 plus something. So the only thing I need to do to get this into that 1 over 1 minus u form is write that as 1 over 1 minus negative x to the 13, right? Subtracting a negative is the same as adding a positive. And now here's my 1 over 1 minus u, the x squared still chilling out front. But 1 over 1 minus negative x to the 13 is sigma n from 0 to infinity, negative x to the 13, all to the m. And again, what makes a constant with respect to the series is that it doesn't have any n's in it. I'll leave the x squared out for now as I simplify inside, but the x squared will be able to come in. Negative x to the 13 is negative 1 times x to the 13. So all of that raised to the n is negative 1 to the n times x to the 13 to the n. So we get negative 1 to the n, and this is x to the 13n. Power to a power is the product of the powers. I can bring the x squared inside now because he does not have any n's in him. And I get negative 1 to the n times x squared times x to the 13n. Should be sigma n from 0 to infinity, negative 1 to the n, x to the 13n plus 2. So remember our geometric series trick, 1 over 1 minus u is sigma n from 0 to infinity, u to the n. And I'm using that here with this as u. So the n is the index of summation. This n shows up at the stage where I introduce the series. Is that what we're asking? Am I? Okay, good. So I haven't done the integral yet, right? I've just written the thing inside as a power series. And that's good news, because now if I want to integrate this function, remember when I was comparing the areas under the partial sums of the power series to the areas of the original function? If I want to integrate that function, I can integrate the power series instead. And that might seem like we're making life harder, but we're really not, because power series are actually incredibly nice to integrate. Again, people get scared of these, but you don't need to be scared of these, because the integral doesn't see the sigma, and the integral doesn't see the -1 to the n. The integral is a dx integral. He's blind to everything that doesn't have an x, so the integral doesn't see any of this. As far as the integral is concerned, we're looking just at that. The integral only sees the x's, so that's integral of x to the 13n plus 2. And the beauty of power series is that the things inside them are power functions. So you can use the power rule. No fancy integration techniques, no trig sub, no partial fraction, none of that. We do always get a plus c when we do an indefinite integral, and I like to write it in front of the series. The integral doesn't see sigma. He doesn't see -1 to the n. He only sees x to the 13n plus 2. And if you integrate any power of x, that's always done by adding 1 to the power. So 13n plus 2 plus 1 is 13n plus 3. And then you divide by that new power. And if you want to write this in that more standard form for a power series, I would put the -1 to the n and 13n plus 3 into a fraction like this. And then you have x to the 13n plus 3. Thoughts, comments? I want to do one more, and then I know we're about out of time, but if you'll bear with me, I'm going to do one more, and then I am going to prime you a little bit for 1110. The reason I didn't have to solve for C in that last one, by the way, and the reason I'm not going to solve for C in this guy, is because I'm being told to just do an indefinite integral. The answer should have a plus C, right? I'm not trying to find a power series for a particular function. I'm trying to find a power series that represents this indefinite integral. So remember, if you're just told to evaluate an integral, you should have a plus C at the end. That's to be expected. The only time you would need to solve for C is when you're trying to find an explicit power series for a particular function, which is something I'll do for you as we cook up power series, but it's not something that you'll need to do in exercises like these. Oh, we don't have the power series for sine yet, do we? That's a bitch and a half. I can't do this one for you. I wanted to do this. This is called a Fresnel integral. They're very fancy. But maybe instead, let's do x squared times the inverse tangent of x squared. Why not? So the game here is to start with the inverse tangent series, which I'll write in terms of the variable u. This was one that we cooked up last time, and we said we need to remember forever. I'm writing this in terms of the variable u because I want a series for the inverse tangent of x squared, right? I want a series for the whole thing inside this integral. And rather than starting fresh, I can start here. So this means if we just plug in x squared for u, I'll get a power series for the inverse tangent of x squared. Which I can then clean up a little bit. X squared to the 2n plus 1, you multiply 2 times 2n plus 1. That's x to the 4n plus 2. So I have now a power series for the inverse tangent of x squared. I want a power series for the inverse for x squared times the inverse tangent of x squared. So I'll take that power series and multiply by the x squared out front. As before, since that x squared has no ends in him, he can come in and out of the series freely. And when I multiply x squared and x to the 4n plus 2, I get everything else staying the same. I get x to the 4n plus 4. Right? Multiply like bases, add the power. 2 plus 4n plus 2 is 4n plus 4. Now we're ready to do the integral. So the integral of x squared times the inverse tangent of x squared dx is the integral of this series. And like we said before, the integral is blind to the sigma. It's blind to anything that doesn't have x's in it. So the integral doesn't see any of this. It only sees this, x to the 4n plus 4. And that's a power rule integral. That's the beauty of this stuff, is that you always just end up integrating straight up powers of x, which is as easy as integrals get. You knew that back in Calc 1. So this will be x to the 4n plus 5 divided by 4n plus 5. And we can leave it like that, or we could group the 4n plus 5 with these over here. And that's where we end up. So integrals as power series are nice. It's actually the reason we did all of chapter 11. Deep down, the world runs on differential equations. Most differential equations can't be solved exactly. It's a sad truth, but we just can't do it. Human beings, we're a little bit clever, but we're not that clever. And differential equations in general are fucking hard. But you can usually take a differential equation, which is an equation involving derivatives of a function, and rewrite them as integral equations. And integral equations are integrals of unknown functions. And you express those as power series and do the integral of the power series, which we always can do. And that will allow you to at least approximate the solution to the differential equation. So next time you're driving over the Sunshine Skyway Bridge, or you're cruising around on the 408 in Orlando, or you get into an airplane, appreciate that none of that would happen without integrals of power series. Genuinely, none of that would happen, because the relevant differential equations that keep the bridge from falling or keep the plane working how it ought to, there's many of them, Navier-Stokes, most famous, are all solved approximately by power series. None of them solved exactly. there are many differential equations we can solve exactly. And if you take MAP2302 with me, I will literally show you all of them. At least all of the linear ordinary differential equations that we can solve exactly, but the vast majority of them cannot be solved exactly, can only be solved by playing these sort of games. And I'll teach you how to play those games in MAP2302 if you can take it. I know we are now 6 minutes over. I am going to try to steal just a tiny bit more of your time because what I'm going to show you on Monday deserves a little introduction. This is a very brief intro to Taylor series. Don't be scared of the name. Taylor series is just a power series. But we call them Taylor series when we use a particular formula to find them. Suppose f of x can be written as a power series centered at 0, sigma n from 0 to infinity, cn x to the n. All right, so somebody already did the stuff that you're doing in 11.9, and they found you a power series. But maybe I don't know what the coefficients are, and I'd like to find these coefficients. We can write out the terms of this power series. That's C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4, and so on. My Calc 2 teacher always, I don't know why, I wish I could stop making this joke. He always called this the dangerous one. Explosive coefficient. I know it's just the worst joke in the world, but it's like a tick. I can't stop making the joke. C4, the military explosive. Okay, I'm sorry. The game here is we don't know the coefficients yet. But if we're very clever, we can come up with a formula for the coefficients by thinking about the derivatives of this function. All right, so again, this is, I'm just writing out, the left-hand side is the same here. I'm just writing out this series. If you plug 0 in, then you get C0 plus C1 times 0 plus C2 times 0 squared plus C3 times 0 to the 4. I'm not going to write the rest of them. That's why C3 times 0 to the 3. You just get C0, which means that the first coefficient of your power series is your function evaluated at 0. So if we're trying to find the coefficients, that's what we want to do. You can get the very first one, C0, the constant term, by plugging 0 into your original function. And if you differentiate this original expression here, star, you differentiate star, C0 differentiates to 0. C1x differentiates to C1. C2x squared differentiates to 2C2x, right? X squared's derivative is 2x to the 1. Just put the 2 up front. C3x cubed differentiates to 3C3x squared. C4 times x to the 4 differentiates to 4C4x cubed. And plugging in 0 here, this guy is gone. Here you get C1 plus 2C2 times 0 plus 3C3 times 0 squared plus 4C4 times 0 cubed. In other words, f primed of 0 is C1. Maybe you can smell where this is going. If I take the second derivative of star, I'm back here, I just differentiate twice. So the first derivative is here. Differentiating again, I get 2C2 plus 3 times 2 times C3x plus 4 times 3 times C4x squared, and so on. Plugging in 0, you just get 2C2 plus 3 times 2 times 0. 3 times 2 times C3 times 0 plus 4 times 3 times C4 times 0 squared. All of these and the later terms are 0. So you get 2C2. So what we've discovered so far is that C0 is f of 0, C1 is f primed of 0, C2, well, f double primed of 0 is 2C2, so this would be f double primed of 0 over 2. And what I'm going to show you on Monday is how to arrive at a nice general formula for Cn. And it will come in terms of the derivatives of the original function divided by something. I'll let you think about what the something is here, evaluated at 0. So that is Taylor's formula. Taylor's formula is a formula for the coefficients of a power series when you can't get the power series any other way. And it involves derivatives. So I'm going to stop here. I'll let you guys go. I got to run to another class anyway. I hope that that showing you a little bit of this helps you get a feel for where those things are going to come from, this crazy ass formula that people are usually so scared of. Don't worry about that for now. I just wanted to drop it in your brain so it can fester over the weekend. Please do worry about your homework. Worry about 11.8 and 11.9. I need you guys to be very comfortable with that material by Monday so we can talk about Taylor series in a way that makes sense. That's it from me. I will see you guys next time. If you want to come by office hours, just a quick heads up, I'm going to be on baby duty for office hours this afternoon. So while I can't talk, I'll be limited in what I can write. But if you do want to talk about anything, come on by and I'll do what I can for you. All right, take care.